Okay, welcome to Robotics 1. In today's class, we are going to start talking about Chapter 8, which is Motion Control Systems. Now, one thing that you should have noticed from all the problems that we solved so far, most of the robots were unstable. In other words, if you were to perturb robot's initial position, robot will not come back to its initial position. So in all the dynamic analysis that we have done so far, if you were to look at the time trace, or say theta versus time, you would notice it went something like this. It didn't come like, it didn't go like back and forth like a pendulum, or it didn't go to all the way to zero again. Now, what I mean by that is I just want to show you a behavior. Say if you have theta dot, which is the angular velocity, and if you have theta, which is the angle. So if you have angular velocity on y-axis, angle on x-axis, this is called as the phase plot. And if you were to plot the phase plot for the robots that we have seen so far, you will notice the phase plot is sort of an outward spiral. So phase plot is an outward spiral. What that tells me is the system is unstable. So this behavior is exhibited by an unstable system. And the robots are naturally unstable because we did not have any control, or we did not control the motion of the joint. Now that is precisely what we are studying in this chapter, is how do we control a robot. So how to control robot. And then there are various techniques. So there is something called as the linear control. There is something called as the nonlinear control. There is something called as optimal control. There is stochastic control. Then there is control based on the neural network. So neural network control. There is fuzzy logic control. There is adaptive control. There is neuro-fuzzy control. And the field of controls is vast. But in robotics 1, we are going to talk about linear control. And the fundamental concept in the linear control are dependent on what are the eigenvalues of the system. So if you recollect, some time ago, I had a discussion on stability. And in that discussion, we talked about eigenvalues. We talked about stable system. So stable system. That could be asymptotically stable. It could be simply stable. And we also talked about unstable system. Now, in today's class, before we get into the details of controls, I have to make sure that everyone understands the concept of stability. What do we mean by eigenvalues? How does the stability depend on eigenvalues? What is the implication of moving the eigenvalues and so on? So let me give you the very basic fundamental principle of linear control. So linear control is controlling the system. And you will see that this is also called as plant. So sometimes the robot, the robotic system that you want to control is called as plant. So controlling the system or the plant by moving eigenvalues. Now, what I'm going to do is, before we dig deep into the eigenvalues and analysis, I'm going to quickly revise what I discussed earlier, because that material is super important. Now, when you try to analyze a system or a plant, there are two ways it can be analyzed. One analysis is in time domain. So in time domain. And the other analysis is in frequency domain. So what do we mean by time domain analysis? For that, I want you to look at the figure that we have here. On the x-axis, we have time. On the y-axis, we have the variable that we are interested in. So in time domain, the independent variable is time. So in time domain, the most important thing is independent variable. Independent variable is time. And in frequency domain, independent variable is frequency. So when you try to understand the response in frequency domain, you will still have a plot which is something similar to this, but here you are gonna have a frequency on the x-axis. And on y-axis, you will have your dependent variable, and we will talk about what dependent variables exist. So now I'm gonna go through the concept of eigenvalue, and I want you to be absolutely clear about this. So first and foremost, the concept of eigenvalues. Now I'm going to start with the same example that I gave you some time ago. Consider that you have a system x dot is equal to ax. Now a is just a number. So this is a first order differential equation. And we want to solve this differential equation. Please observe the independent variable is time. So what it means is we are trying to analyze this system in time domain. So eigenvalues are important, or they are considered when we look at the time domain. Now what I want to do is I want to solve this system. And I worked out this example earlier but I just want to explain this once again. So this equation becomes like this. I need to separate the variables so that this equation can be solved. So I would have dx over x is equal to a dt. And now I need to integrate left and right. When I integrate the left hand side, I have ln of x and I have a t plus c, where c is the constant of integration. Now what we need to do is we need to find out the relationship between x and time, because note, our independent variable is time. So the solution of a differential equation is a function x of t. Once you substitute that function on the left hand side and right hand side of equation 1 gets satisfied. So what I'm going to do is I'm going to take the exponent. So I would take e here and I will take e here. Exponent logarithm gives me x of t. That gives me e to the power at plus c. This equation can be written as e to the power at, e to the power c. Please note e to the power c is constant. So I can write this equation as a e to the power at. So this is the equation x of t is equal to e to the power at times a. Now I want you to think about few cases. The first simple case that I want to talk about is when a is equal to 0. In last few lessons, we have been talking about this, but in today's class, what I want to do is I want to show the phase plane. So if I were to plot x versus time for a is equal to 0, at time t is equal to 0, value of x is going to be a, and that value would remain constant as the system goes. So value of a is going to remain constant. Now next thing is I want to look at when if I were to look at x and x dot, please note if x is equal to a, x dot is going to be 0. So if I were to draw this on the phase plane, I'm gonna kind of look something like this, because as time goes on, it's just going to be a single spot at a. So if a is 0, it would be here. If a is non-zero, it's going to be here. If a is somewhere here, so you're gonna have a and you're gonna have 0. So it's just gonna be one spot. So depending upon the value of a, if the, so just to make it clear, this is the point a comma 0. Now I want you to look at the case when a is less than 0. When a is less than 0, you have time, you have x. You will start at time t is equal to 0. The value is going to be capital A. And then as time goes on, it's going to go like this. So this is how will be a e to the power at when a is less than 0. Now let's see what happens in the phase plane. In the phase plane, you would start with some non-zero x, and say non-zero x dot. So I'm going to draw the phase plane in 4 quadrants. You may start with x and x dot somewhere here, and you would realize that you will approach the origin. So as time goes on, your x value will go to 0. Your x dot value will also go to 0. So please notice this behavior is inward. Now, if you were to look at when a is greater than 0, when a is greater than 0, you would start x, and if you have time over here, and I'm gonna show the same plot in phase plane, x, x dot. So you would start with a, and then it will go up, a, e to the at. Now, if you look at the way this system will behave, this system would behave something like this. So this is outward. So if you look at the 3 different behaviors, when the eigenvalues or value of a is 0, then the system is going to have just a point. So what it means is system is simply stable. So this is a simply stable. So this is simply stable. This is asymptotically stable. And this system is unstable. So before we get into the stability, this is super important. Now what I want you to understand is in this entire thing, the sign of A made all the difference. What it means, when A was 0, the system was simply stable. When A was less than 0, the system was asymptotically stable. When A is greater than 0, system became unstable. Now, I want you to remember this important concept. Now, here comes the concept of eigenvalues. So, why eigenvalues are super important? Now, if you look at an equation, set of equation, and I'm gonna do this analysis once just so that we understand what is going on. Consider a simple spring mass damper system. So you have mx double dot plus kx is equal to 0. This system we studied multiple times. So this is mass m, this is the spring stiffness k. Now this is the second order system. Second order system. Now what I want to do is, and probably you have noticed this, when we try to study the ODE and when we try to study the uh, Lagrange equation, the final answer was in the first order form. So I'm gonna use that transformation to write this second order system into a first order system. So I'm gonna write this second order system into a first order form. What do I mean by first order form? Is please note the highest order of derivative here is 2. So I want to convert that into 2 first order equations. So here is the process. So start with the variable with 0th degree. What it means is in this equation, here the order of x is 2. There are 2 dots. Here is the variable that does not have any dots. So that is going to be my first variable. The derivative of the first variable is going to be my second variable. So I have these 2 variables. This is the displacement variable and this is the velocity variable. Now what I'm going to do is I'm going to write this equation something like this. So I'm going to say derivative of displacement is velocity. So check this out. D by dt of x is equal to x dot. So this simply means, what this means is derivative of displacement is equal to velocity. Now what I'm going to take is I'm going to take the velocity expression and then I'm going to see what is d by dt of velocity. And d by dt of velocity is, I want you to notice, and I will do this calculation here, d by dt of x dot is actually x double dot. And I need to find out the value of x double dot. This x double dot is present in this equation. So I can actually use that equation just like this. Check this out. I can say mx double dot plus kx is equal to 0. So I would write down x double dot is equal to minus k divided by mx. In other words, this equation can be written as minus k by mx. So I would go ahead and write this equation here, minus k by mx. So if you look at equation 1, this is my equation 1. This equation was written in the second order form. That equation we converted in equation 2 in the first order form. Now, some of you may say, hey, what is the advantage of this jugglery? This jugglery is super duper important because that allows me to write this equation 1 into a matrix vector form like this. Check this out. X dot d by dt is equal to, I have this matrix and I have x dot. Now please note that I have the same variables on the left hand side and the right hand side, except I have the derivative of the variables on the left hand side, and these are called as the state variables. So I have the derivative of states on the left hand side and I have the states on the right hand side. So derivatives on the left hand side. So this equation can be written as, and I want you to follow this very carefully, as minus k by m 0. So now if you expand equation 3, like first row, first column, you are gonna get the first equation. If you take the second row multiplied by the first column, you're gonna get the second expression. So what has happened now is we have converted this second order expression into its equivalent first order form, and this is what MATLAB needs. So if you ever try to solve a differential equation using MATLAB, the differential equation needs to be written in the first order form so that MATLAB can solve it. However, here is a good news, and we will talk about it in next class. MATLAB has provided a code generator, just like Euler-Lagrange. So there is a code generator that will take the equation in the second order form and convert those equations into first order form. And we will talk about it in next class. But I want you to understand what has happened here. Now I have a vector, and I'm gonna call this vector as X. This is a vector. I have a matrix and I have another vector. So this expression is now written as a matrix vector expression. And before I go any further, I want you to see that what I have shown here, equation, this equation in this rectangle is similar to the expression that I have in this rectangle. The difference being the expression here is a scalar equation, which means X is just 1 by 1. A is just a number. But here, X under tilde is a vector and A is a matrix. Now, even though we have a matrix, the solution process is actually almost similar. And I will try to give you more physical interpretation and understanding than the rigorous mathematics. So think about it, that I have now, I want you to think about, you have X dot, this is a matrix X. So you have X dot is equal to AX. And now I want to solve, how to solve this expression. But it's actually simple. In the previous case, what we did, we had an exponent, we took the exponent of the scalar quantity. In this particular case, we have a matrix. So what I'm going to do is, I'm going to take a matrix exponent. So it's going to be matrix exponent A times T multiplied by the value of X naught at time T is equal to 0. So this is the initial condition. And this is the matrix exponent. And this is how you can solve a linear differential equation. So the idea is, if you have an equation, if you convert that into the first order form, if it's a time invariant constant coefficient differential equation, I need to write this down, time invariant, which is nothing but constant coefficient linear differential equation, you can use this matrix exponent and solve this system. Usually, since it's a matrix vector, this term is usually here. So this is the initial condition. And that is how the problem can be solved. Now, here comes the concept of eigenvalues. Now, eigenvalues are actually, they show us the characteristics of the matrix. So that's why if you look at the eigenvalues, they are determined from the characteristics equation. When you studied linear algebra, you find characteristic equation, and from characteristic equation you can find out the eigenvalues. And depending upon whether the eigenvalues have negative real part, so eigenvalues, first and foremost, eigenvalues could be real or they could be complex. So what do I mean by real? Real means a number 1, 2, 3, 4, or -1, -4, something like this. Complex means 1 plus 3i, or -1 plus 3i, or -1 minus 4i, and so on. So the eigenvalues could be real or eigenvalues could be complex. If the eigenvalue has zero real part, if the eigenvalues, they have zero real part, I want you to correlate this with the case, first case, system is simply stable. So system is simply stable. So if the eigenvalues have zero real part, the system is simply stable. If the eigenvalues have negative real part, then the system is asymptotically stable. And if the eigenvalues have positive real parts, the system is unstable. Now, it's customary to show the eigenvalues on a complex plot. So consider I have eigenvalues. Say I have eigenvalues, say -1. I have eigenvalue, say -1 plus 3i. I have eigenvalue 1 plus 3i, and I have eigenvalue 4. So these are the eigenvalues I have. So it is customary to show the eigenvalues on a complex plane where you have the real part of the eigenvalues. Eigenvalues are called lambdas. Real part of the eigenvalue here, and the complex part or the imaginary part of the eigenvalue here. Now, one thing that I want you to notice, so let's see, if you have eigenvalue -1, this eigenvalue is over here. So this is going to be my first eigenvalue. Second eigenvalue is -1 plus -3i. So -1, what I do is I have the second eigenvalue. So this is 3. This is -3. So this is -1 plus 3i. This is -1 minus 3i. And then the last eigenvalue is 4. So I'm going to plot this eigenvalue 4 over here. Now, please notice, if your eigenvalue is on the left half plane, and I need to write this something like this. If your eigenvalues are here, system is asymptotically stable, which means as time goes to infinity, x dot goes to 0, x goes to 0. That's what I mean by asymptotic stability. So if you were to plot the response, you would see something like this type of response. Now, the next thing is, if you have eigenvalue somewhere over here, so this is what will happen if you have eigenvalue over here. If you have eigenvalue over here, then what's going to happen is there won't be any oscillation, but the system will actually go down to 0 like this. If you have eigenvalue over here, in this region, the system is going to be unstable. So this is unstable. And let me show you what happens if you have eigenvalue like this. Your response is going to be like this. Let's take one more case. If you have eigenvalue, say somewhere over here. So this eigenvalue is 4 plus 3i, and this eigenvalue is 4 minus 3i. Then your response is going to be something like this. So remember, whenever you have an imaginary component, imaginary component causes oscillation. And some of you may ask me, wow, why is this oscillation present? So what I want to do is, I just want to give you a simple example. Think about, in the scalar case, think about if your value A is something like 4 plus 3i. Imagine if your value A is 4 plus 3i. So then what happens is, when you have x of t, which is e to the at. Now e to the at is going to become e 4 plus 3i t multiplied by, say, x naught, which is the initial condition. This becomes e to the power 4t multiplied by e to the power 3i t multiplied by x naught. Now I want you to focus on this number. This is, if you consider e to the I theta is equal to cosine theta plus I sine theta. So this becomes cosine of 3t plus I sine of 3t, which means you have logarithmic increase by the first term, log increase or exponential increase. You have exponential increase because of the first term, and you got sinusoidal behavior or harmonic behavior or oscillations due to the second term. Now what I want to ask you is, what would happen if this number is negative? If this number is negative, please note nothing changes. Cosine of minus 3t is nothing but cosine of 3t. Sine of minus 3t becomes a negative number here. But still the oscillations remain. So remember the eigenvalues where they are in this uh, complex plane. This is also called as the complex plane. They dictate the behavior of the system. Now, I want to take the example of the robot systems that we studied. The robots that we studied, most of them had eigenvalues that were on the right hand side. So most of the robots, eigenvalues were somewhere here. That's why the system response was either oscillatory and growing or exponentially growing. If we want to design a motion control system, then what we should do is somehow we should transfer the eigenvalues from the right hand side to the left hand side. So this is the fundamental purpose of the motion control system, that we want the eigenvalues to go from the right hand side on to the left hand side. Now, how would you make this transition happen? How would you push the eigenvalues to go from right half side to the left half side? And that is done by multiple ways. You can add some sort of PID controller. So if you add a PID control, the purpose of the PID control is to move the eigenvalues from the right hand side to the left hand side. You can actually add maybe some damping element that will actually dampen the behavior of the system, that it actually does the exact same thing, moving the eigenvalues from the right hand side to the left hand side. Now the other control what you can think about is something called as the state feedback. So you can actually come up with some sort of state feedback. You can come up with some sort of state feedback that would actually achieve the exact same thing. Now, how you achieve this is depends upon the tools that you use. So you could actually use the tools in the time domain, or you can use the tools in the frequency domain. So what I want to do is I want to come up with a simple controller idea and talk about it in just a minute. But before I go uh, to uh, to analysis, are there any questions at this point related to eigenvalues? So remember, all the linear controls technique, they cause eigenvalues to move. This is what we want. And in the time domain, we call them eigenvalues. In time domain, once again, what do I mean by time domain? Time is independent variable. And in frequency domain, frequency is independent variable. And we will study this in detail, but in time domain, we have eigenvalues, and in the frequency domain, they are called poles. So basically, whether you use time domain or you use frequency domain, at the end of the day, you are trying to change the location of eigenvalues or location of pole. And this is so important that I need to state this again. Linear control techniques, whether they are in time domain or whether they are in frequency domain, the fundamental purpose is to move location of eigenvalues or poles to desired place. Because I just want to tell you here, if your eigenvalue, so imagine that, let me draw one more figure. Say you have your eigenvalue here. Okay, the system eigenvalue is here. Then everyone agrees that the system is unstable. Now what I do is I add some sort of control algorithm. It could be PID, it could be pole placement, and move this eigenvalue somewhere over here. So this is the location where the eigenvalue got moved and the system became stable. Now please note, I again add some additional controller and move this eigenvalue further onto the left hand side. So this eigenvalue got moved from location 1 to location 2. Please note the system became more stable. So this gives me an interesting concept which is called as the stability margin. So stability margin is, please understand, the system was unstable at say location 0. System was unstable at location 0. As soon as it crossed this vertical line, this is the real part of the eigenvalue, this is the imaginary part of the eigenvalue. As soon as it crossed this vertical line, the system became stable. So it tells me how far the system eigenvalues are from the imaginary axis. That tells me how stable the system is. So this distance is nothing but stability margin. And why is this stability margin important? Because please try to understand that sometimes you want your robot to be super stable. So that means in that case, you want to push the eigenvalues towards very left side of the imaginary axis. So linear control techniques or the motion control techniques that we are going to study will talk about how the eigenvalues get moved. Now, in sometimes when we are going to study in the frequency domain, we are going to study movement of eigenvalues or poles with respect to a parameter. So for an example, you say you have a gain, and then the question is, if you change the value of the gain, how does system eigenvalues change? How do they go from left to right? Or they go from right to left? But we will talk about all these concepts in detail. But before we go any further, I just want to think about a very simple motion control design. Say, let's consider that I have a spring mass system. I have a spring mass system. This is K, this is M. And right now, there is no damping, there is no air, and we studied that if there is an excitation, if I pull this mass and let it go, the system is going to oscillate something like this. And if there is no damping, this oscillation will continue for the infinite period of time. If I were to draw the phase plane, which means if this is the displacement versus time, if I have the displacement on x-axis, if I have the velocity on y-axis, I would notice that there will be a circle. And this circle is not going to grow. This circle would remain a circle. Now, what I want you to think about is now, same spring mass system, and I add a damper. Same spring mass system, and then now, but in addition to spring, I have a damper C. Now, what will happen because of this damper is as the time goes on, the response will decay and it will become zero after some time. So in this case, you would notice that this will become like an inward spiral. This will become an inward spiral. So if the damping is positive, the system response is going to become inward spiral. Now consider the case that now instead of positive damping, we have a negative damping. And this is an interesting case. What happens is, which means every oscillation, damper, rather than taking some energy out, it's pumping energy into the mass. So this is negative damping. So what it means, in every oscillation, in each cycle, damper adds energy. So clearly, you can guess that if in each cycle, damper is going to add energy, then clearly the system response is going to grow. So if I were to draw the phase portrait or the phase plane, it's gonna be an outward spiral that tells me the system is unstable. It's gonna show me inward spiral here that tells me the system is stable. And then here closed circle that shows me the system is simply stable. Now, how do these system eigenvalues, uh, uh, how do we use system eigenvalues to decide all this? Now, for that, what I'm going to do is, I'm just going to give you a simple trick. Let's look at the equation of motion. The equation of motion is mx double dot plus cx dot plus kx is equal to 0. Now what I want to do is, I want to write this expression into the state space form. So to step 1, when we do the state space, is find out the variable that does not have any derivative, no dots. So this is my first variable. This is my second variable. Now why do I need two variables? Because please note, the highest order of derivative here is 2. That's why I need two variables. And then my first expression is going to be d by dt of x is equal to x dot d by dt of x dot. Now check this out. In this expression, this is going to become minus c by m x dot minus k by m x. And I will give you a minute to think about this transformation. So what I did here is I rewrote this expression x double dot is equal to 1 by m minus cx dot plus kx. And that expression is written over here. So now what I'm going to do is I'm going to write this expression in the first order form. But please understand, we have damping present. So in the first order form, this equation is going to look like x dot d by dt is equal to 0, 1 minus c by m minus k by m, and then I would have x and x dot. Any questions here? So this equation is exactly same as the equation that we looked earlier, except in the initial equation, the earlier equation that we looked, and that equation was here, I did not have a damper. Oh, did I make a mistake? Yes, you are right. You are right. I made a mistake here. So this is K and this is C. Correct. So this is the expression. In the previous case, the value of C was 0. Now what I'm going to do is I am going to find the eigenvalues. And to find eigenvalues, I'm just going to assume m is equal to 1. That will make my calculations easy. So I have a matrix. This matrix A is going to look like 0, 1, minus k minus c, because m is equal to 1. Now I want to find out the eigenvalues. How do we find out the eigenvalues of the matrix? So what we do is we say determinant A minus lambda I is equal to 0. We solve this equation, determinant of A minus lambda I is equal to 0. So I'm going to solve this equation. This equation is going to look like 0 minus lambda, 1 minus k minus c minus lambda, and I need to find out the determinant of this matrix and equate that to 0. Let's do that. So I have minus lambda minus c minus lambda minus of minus k is equal to 0. So determinant of a 2 by 2 matrix, if I have a 2 by 2 matrix which is A, B, C, D, the determinant of A, B, C, D is A, D minus B, C. So what I did is A multiplied by D, which is minus lambda multiplied by minus C minus lambda. So going forward, this equation becomes lambda C plus lambda plus K is equal to 0. That gives me an expression lambda square plus C lambda plus K is equal to 0. Now these lambdas are the eigenvalues. Lambdas are the eigenvalues. So I'm going to try to solve this expression. And please note, this equation you will see again and again in multiple ways, in multiple contexts. When you solve the frequency domain, you will get the same equation. Remember this: lambda square plus c lambda plus k is equal to 0, where c is damping and k is stiffness. So this expression can be solved with the expression. So let me write this down: lambda square plus c lambda plus k is equal to 0. Value of lambda is, looking at the quadratic roots, minus c plus minus square root of c square minus 4a, a is 1, 4k divided by 2. Now, so this is the equation that we have. If I were to look at, if m was not equal to 1, if m is not equal to 1, the expression that I will land up with is m lambda square c lambda plus k is equal to 0, wherein lambda is equal to minus c plus minus square root of c square minus 4mk divided by 2m. So if your m is not 1, I just did m is equal to 1 in this expression, just to make it simple. So in this expression, please note m is equal to 1. If m is not equal to 1, if you keep m as is, you will have this expression. Now let's understand the conditions that we looked at earlier. So condition 1, in the first case, c was 0. So case 1, c is equal to 0. When c was equal to 0, lambda became plus minus square root of minus 4k. Now this tells me that, again, this is an imaginary value divided by 2. So this gives me plus minus square root of k I. If in this same case, if m was not equal to 1, then I would get lambda is equal to plus minus square root of k by m I. So as you can see, the eigenvalues are purely imaginary. So here, eigenvalues are purely imaginary. What that means, zero real part, which means the eigenvalues, please note, these are complex conjugates, are at these two locations. What it means is you are going to have a purely oscillatory response. And that is what you observe in the case of a simple spring mass system. When the damping coefficient is 0, you are going to have a purely oscillatory response. Now let's look at the second case, wherein you have case 2, positive damping. So I have positive damping. Which means C is a positive number. If C is positive, let's look at again the equation for lambda. Lambda is minus C plus minus square root of C square minus 4k divided by 2, or lambda is equal to minus C plus minus square root of C square minus 4mk divided by 2m. So when C is positive, I'm gonna get two roots. The first root is going to be minus C plus something like C square minus 4k. This is a number, so I'm just gonna call this maybe omega I, and then plus C minus omega I. Oh, this will be minus C plus omega I. And what this means is I will have two roots, and these roots will be in the negative part. So in other words, it will be here. So system, if you were to look at the system behavior, system is going to be asymptotically stable. Now let's look at the last case. If you look at last case, I have negative damping. So negative damping where C is negative. Lambda is equal to minus C plus minus square root of C square minus 4k divided by 2m, or lambda is equal to minus C plus minus square root of C square minus 4mk divided by 2m, if m is not equal to 1. So here you will notice that we have this negative C. Since C is negative, what it means, it's this number is like minus 2, minus 3, minus 4, etc. You are gonna have positive value of real part. So this value will become positive. So you are gonna have C plus minus I omega. Now what that means is your system is going to be somewhere over here. This is omega. And that means the system will be unstable. So if you look at the system behavior, this is how it's going to look like. And I just want to collaborate this with the information. So yeah, left side doesn't need correct, bottom end correct. So I just want to tell you that I derived the exact same equation for the second order form, which means if you recollect the earlier lecture, instead of converting the system into the first order form, I directly went ahead and made the substitution e to the lambda t, and this equation became m lambda square e to the lambda t plus c lambda e to the lambda t plus k e to the lambda t is equal to 0. This equation landed up with m lambda square plus c lambda plus k is equal to 0. And this was discussed in earlier lecture. And then we tried to solve the equation again here as this quadratic equation, and we obtained the exact same results. The results, whether you obtained in the state space form or the first order form, they mean the exact same thing, that you have eigenvalues that are purely imaginary, which means zero real part. They are simply stable. If the eigenvalues have negative real part, these are asymptotically stable, and the eigenvalues that are positive real parts, that are unstable. Okay, I'm gonna stop here today, but I would be happy to answer any questions that you may have. Just raise your hands and I would be happy to answer questions. Okay, now this is a question I would like to answer. Some clarification on material on quiz 3. So quiz 3. I don't think you will have any problem is solving the first point, which is kinematic diagram. There is one more quiz, quiz number 4, that will be posted on Thursday. Perform forward kinematics, perform inverse kinematics, and finding the differential equation of motion using MATLAB. That you should not have any problems. The last part is solving differential equation using following values, that you have to use your judgment. So here is what is given to us. And first and foremost, this is actually a super simple problem. This is not a difficult problem at all compared to the problems that we actually solved so far. What you have is you have an inner rod I1, and you have an outer rod I2. And in this particular case, I1 is given as 1, I2 is given as 1, M1 is given as M2, that is given as 0.5. Now, first and foremost, we have to make some assumptions. The first assumption that I'm going to make is it's a slender rod. So link 1 and link 2. So assumption is link 1 and link 2 are slender rods. Now, when I make that assumption, I have an expression which is I1 is equal to M1 L1 square by 12. I2 is equal to M2 L2 square by 12. Now, from here, I can find out the value of L1 and I can find the value of L2. And that can be easily seen that it's going to be like square root of 24, and this is going to be square root of 24. Now, some of you may ask me, what is this dimension? This dimension is this. This is L1, and this is actually L2. Now, the next question is, value of theta dot is given. Value of theta 0 is given. So theta is this angle. This theta at time 0 is given as 45 degrees. Theta dot at time t is equal to 0 is given as 10 degrees per second. But the question is, the value of r and r dot is also given. What is this r and r dot? Now for that, I want you to visualize something like this. The CG of the second link. This is the CG of the second link. This is the CG of second link. This is the CG of the second link, and this distance is nothing but r. This distance is nothing but r. So what this tells you is, whenever you are trying to solve this problem, you are going to have differential equations in theta dot, and you will have differential equations in r dot. So your initial value for when r is equal to 0 is going to be 0.5 meters. R dot at 0 is going to be 0.1 meters per second. So what this tells me, and some of you may ask me, hey, this R 0.5 is too small. And that's okay, because you can visualize this rod to be something like this. So you have this robot wherein you have initially this robot, this length is something like this. And as this robot turns, this sort of starts extending, and this goes forward. So from solution point of view, you will not have any problem. Your r is 0.5, which is the initial distance from the origin, and r dot is the velocity. So when you try to draw the kinematic diagram, your d values, d0 and d dot 0, will be 0.5 and 0.1. So with this, you should be able to solve the problem. I'm gonna stop recording here, but I would be happy to answer any more questions you may have.